In this section, we're going to look at short reinforced concrete compression members. These members will only have axial load, and we will have no global buckling concerns. By the end of this section, you should be able to explain how short reinforced concrete columns progress to failure, describe the three primary roles of transverse reinforcement in columns, explain how the concrete cover and core will behave as the column progresses to failure, and how we account for their behavior. Explain and illustrate the different buckling modes of longitudinal reinforcement and how these influence minimum transverse reinforcement size and maximum spacing requirements in ACI 318. Use the given expressions and plots to account for buckling of steel in the stress-strain response. Differentiate between well-confined and poorly confined column behavior. Develop a load deformation plot for a short column incorporating confinement and reinforcement buckling. And finally, identify poorly detailed columns and recommend improvements. In this section, we're going to look at how confinement affects the behavior of our short compression members. A short compression member has only axial loads and no global instability concerns. So later we're going to talk about short columns, which have axial loads and moments, and then also slender columns, which will have axial loads, moments, and global buckling concerns. But right now we're just looking at axial only members with no global instability concerns. We're next going to step through how these axial only members will progress to failure. They'll start with an elastic stress-strain response. So as the axial load on the column increases, the local strains or stresses in the outer concrete cover increase until they reach some limiting value. So we're going to be elastic until we lose the cover of our concrete. At this time, the limiting strain or stress of the exterior cover cracks so that no longer can support the appreciable load, or it spalls off. So at the end of step 2, or at step 2, we lose our cover concrete and we only have our confined core. Any additional stresses are on the confined core and the reinforcement. Then the steel begins to yield or buckle, the longitudinal steel. After this, the additional stress will be on the concrete core because the longitudinal steel won't be able to take any additional stress. Eventually, the core reaches its ultimate strength, or we have some kind of failure of our ties that are confining our core. And then finally, our column fails. So we'll look at all these steps individually on the following slides. First, we have our elastic stress-strain response range. When we first apply load, we're going to have elastic behavior in our concrete and in our steel. So we can we can relate our strains to our stresses by our modulus of elasticity. So linear elastic material. Also note that we'll have the same behavior in both our cover and our core concrete because we won't have any confinement effects taking place yet. Our materials will start to go inelastic, and then we'll eventually lose our cover concrete. When the strain in our cover concrete passes the ultimate strain, the cover is going to spall off. So where we had the complete section before we were at epsilon CU, after this we lose our cover, and we only have the core remaining to resist load. Additional stress will then be carried by our concrete core and our longitudinal reinforcement. Our concrete core can handle these additional stresses because of the benefits of confinement. Our longitudinal steel will then either yield or buckle. If our longitudinal steel yields, we're going to have a little more of a ductile response as we'll progress out on the yield plateau for the steel. If our longitudinal steel buckles, we're going to decrease in its load carrying capacity, and this can lead to a brittle failure of our column. Buckling of the longitudinal steel can either occur between stirrups or it can occur across several stirrups. And we'll look at later in this presentation how to account for and how to prevent buckling of our longitudinal steel. As our longitudinal steel buckles or yields, additional stress and loads are going to be carried by our confined concrete core. So as we drop off in stress or progress on our yield plateau, our column will continue to gain strength or have additional strength because of additional load being carried by our concrete core. Eventually, our concrete core is going to reach its ultimate strength, and then the column's going to fail. This can be triggered by crushing of the concrete or fracture of one of the stirrups that are confining the inner core. After the column reaches its maximum strength, the column can no longer hold additional load and it's going to fail. Failure is typically triggered by the failure of the core, which is generally caused by fracture of the confining reinforcement. When our confining reinforcement fractures, our core is no longer confined and it causes a quick failure of our column. Within this failure mechanism, our transverse reinforcement is going to play three roles. First, it's going to resist the state of stress or strain in the concrete in the zone adjacent to the tie. So these are our shear stresses. Any transverse reinforcement that crosses our shear cracks is going to resist these shear stresses. Next, our transverse reinforcement is going to increase the strength of our concrete core. This transverse reinforcement will confine our concrete core if detailed correctly. Finally, the transverse reinforcement is going to provide buckling strength of the longitudinal reinforcement, particularly when the concrete cover may be lost due to some type of accidental damage or because it's overloaded. So essentially, before the cover falls off, the cover will help resist the buckling of our longitudinal steel. After we lose the cover, the steel wants to buckle out, our longitudinal steel wants to buckle out, and our transverse reinforcement is going to keep it from buckling or pull it back in. So I illustrate that in these two figures. Next, we're going to look at the behavior of our cover and our core concrete. Initially, our cover and core concrete are going to behave the same. So looking at our stress strain curve, they'll behave the same. At some point, our cover is going to progress towards its ultimate strength. It's unconfined, so it's going to spall off and it's going to fail and spall off. Our core is going to kind of transition from our unconfined behavior to our confined behavior. So this would be our actual core behavior here. Theoretically, what we'll do is just assume that it follows the stress strain curve for our confined concrete that we found in the previous section. We'll account for the loss of cover by decreasing the area of our concrete. We can see when we start, our column will have the full area of concrete, so the full B times H. When we lose our cover, we're going to decrease this area linearly until we get down to just the confined inner core. Generally, we'll start losing our cover at our ultimate strength or ultimate strain, and it will completely spall off at a strain of around 0.004 to 0.005. After the cover falls off, it is no longer able to provide buckling restraint for the longitudinal reinforcement. When the cover falls off, the transverse reinforcement restrains buckling. Depending on the size and spacing of our transverse reinforcement, we will either see buckling between hoops, as shown here, where we'll see buckling between our transverse ties or hoops, or buckling across several hoops. And in this case, we're going to have yielding of intermediate ties that allow for this buckling to happen. Again, the buckling mode will depend on the spacing and size of the transverse reinforcement. Buckling across multiple ties can be determined based on the stiffness provided by the transverse reinforcement and the spacing of the transverse reinforcement. So essentially the spacing of the transverse reinforcement and the stiffness of the transverse reinforcement is going to control what buckling mode we see. Next, we're going to look at how to provide adequate tie spacing to prevent buckling across two ties. We'll start the derivation for our length or spacing requirements by starting with our critical buckling stress. Our critical buckling stress is just pi squared E over KL over R squared. Our E in this case is our tangent modulus. Our K is our effective length factor, which modifies our buckling stress from a pin-pin case to whatever case we're looking at. So we'll see what's an appropriate effective length factor for us. And then our L in this case is the distance between our ties or our tie spacing. We know our R for a circle is dB over 4, so we're also going to use that. We can plug R equal to dB over 4 and L equal to S into our critical buckling stress expression, which will give us this equation here. We can rearrange it a couple times to give us an equation relating our spacing to the diameter of our reinforcement. Bresler and Gilbert recommended several different factors that we can use for our bracing in non-seismic regions before our steel yields. We're going to plug in K equal to 0.7, ET, so the stiffness of our steel at 29,000, and then FCR, our F critical is 70 KSI. Plugging that in, we'll get a spacing to diameter of bar ratio of 23. The ACI specified limit is a little less than this 23. So the ACI limit is at 16 here. Bresler and Gilbert also recommended a couple factors that can be used for the bracing after our steel yields. After our steel yields, our stiffness is going to be substantially less. On our yield plateau, we won't have any stiffness, and then in our strain hardening region, we'll have a stiffness much lower than our initial elastic stiffness. So they recommend here a K of 0.7, modulus of elasticity of 1500 KSI, and an F critical of 70 KSI. So that'll give us a S over dB spacing limit of 5.2. The actual behavior of our yielded steel is going to be somewhere between the yielded and non-yielded case. And we'll talk about that later in this presentation. As I said on the previous slide, the actual behavior of our yielded steel is going to be somewhere between the yielded and non-yielded case. One way of determining our stiffness is we can create an equation for our post-strain hardening behavior, and then know that our stiffness is just the slope of this equation. So we can find our ET as just the derivative of this expression, which is shown here. This procedure is called the tangent modulus method. And within it, we're assuming that the entire bar is yielding and the entire bar has the same strain. Many tests have shown that the tangent modulus method is far too conservative. This is because when a bar buckles, we'll have an unloaded side and a side that's further loaded. Our further loaded side is going to progress into that inelastic range, that strain hardening range like we saw in the previous slide. The unloaded side, on the other hand, is going to be moved back into the elastic range. So we're going to have a different stiffness on each side of the bar. We'll have additional loading and yielding on one side of the bar, and unloading and non-yielding on the other side of the bar. So a reduced modulus method was proposed to account for this behavior. The reduced modulus is taken as about 3 times the tangent modulus. So our ER is equal to 3ET. If we use all of these expressions that I've shown over the last couple slides, we can get the plot shown here, where we have a stress versus strain relationship for several different spacings. We see that the closer spacing that we have, the closer it resembles our conventional stress-strain relationship for steel. The wider the spacing, the more likely it is for that longitudinal steel to buckle. So if we have an S over dB equal to 11, we're going to have buckling of our steel. So after we yield, we're going to decrease in stress as we increase in strain. So these curves can be used to account for buckling. Next, we're going to look at how to provide an adequate tie size to prevent buckling across two ties. We looked at length already, or spacing, so now we're moving to the stiffness of our ties, which is normally governed by the tie size. Buckling can occur in two different possible modes. The first mode of buckling is across two ties here. So this tie is not preventing buckling. The second mode of buckling is shown here, where the tie prevents buckling and causes this second mode to occur. The second mode of buckling is going to require a much larger load to buckle, which means our bar is going to have a higher capacity. So we want to have enough tie stiffness to force the second mode of buckling to occur. Bresler and Gilbert found this relationship between, or this ratio of the tie diameter to the diameter of the longitudinal reinforcement required to force the second mode of buckling. So this relationship is dependent on the length of the tie and the tie spacing. Note that a tie is going to be most effective at restraining buckling if it's close to one of its transverse legs. So here, these corner bars, they have a leg of the tie extending right next to the bar. So these bars are going to be most effectively restrained from longitudinal buckling. This bar in the center is going to have, the tie is going to be less effective at restraining buckling here. So our B here, the length of our tie, is the length from the center to center of these bars that are restrained from buckling. So this is the B that we use in our Bresler and Gilbert expression. Bresler and Gilbert further simplified their expression to this expression here, where the diameter of our tie needs to be greater than 15% of the diameter of our longitudinal bar. This is equivalent to the ACI minimum transverse tie sizing. So in ACI, we have limits for our transverse tie size. If we have longitudinal bars of number 10 or smaller, we need a number 3 tie. If we have longitudinal bars of number 11 or larger, we need a number 4 transverse tie. Next, we're going to look at the axial load deformation response. We'll talk about it generally, and then we'll actually put together some axial load deformation responses for columns. So a column is either going to respond by hardening or softening as it's loaded past the elastic range. And this depends on the detailing of the column, specifically the spacing of our transverse reinforcement. If we have a well-confined column, in other words, that we have a properly sized stirrup at an adequate spacing, we're going to have a hardening response. And we'll have cover that falls off of most of our column. And you can see here we have buckling of some of these reinforcement or fracture of some stirrups, but this happened after we had a hardening response. If we have a poorly confined column, in other words, if we have improperly sized stirrups at inadequate spacing, we're going to have what's called a softening response and a localized failure. So this is a poorly confined column with a localized failure and a well-confined column with more of a global failure that occurs. Here you can see the difference in our load deflection responses for our localized and global failure, or our softening and hardening response columns. You can see in the column where we had improper sized stirrups spaced too far apart, we had a localized failure. So after we lost our cover concrete, our longitudinal steel buckled. So here we were going up elastic, then our concrete started to go inelastic until we lost our cover concrete. At this point, our steel can't take any more tension or can't take any more compression and it buckles. So our column loses strength and we have a localized failure. In our hardening response, after we lose our cover, our concrete core is going to be confined and we're going to have an increase in strength. Our longitudinal steel is still going to be able to take more load because it's not buckling, and our concrete core is going to be able to take more load because it's confined. So at some point here, we're going to reach the maximum strength of our concrete or the yield strength of our steel, and then we're going to drop off until we have a fracture of one of our transverse ties. On the next couple slides, we're going to find the axial load deformation response for the column we've been looking at. To calculate the load deformation response, we're going to use the same procedures that we did before. Here I set up an Excel sheet, and I'm going to show you how the different columns relate. The first thing that you can see is we're going to relate the strain in our total column to the strain in our core concrete using the confinement relationships that we found in our section 5. Or our section on the confinement of reinforced concrete. These equations are from Mander, Park, and Priestley. We can use a conventional stress-strain relationship to go from the strain in our column to the stress in our cover. So here I'm just going to use the Todeschini et al. Relationship that we looked at before. Note, I have another column in the Excel sheet here to account for the loss of the cover concrete in our section. Before our epsilon C naught, we're going to have the full area of our cover concrete, and I'm going to vary our cover linearly from the point when it starts to fall off to a strain of 0.004 or 0.005. And then after 0.004 or 0.005, the area of my cover concrete is going to be 0, as I only have core concrete left. We're going to use the same linear elastic relationship for our steel to relate our strain in our column to the stress in the steel. So under the yield stress, our steel stress is just going to be equal to our column strain times our modulus. After our yield, we're going to use the expressions from Pantazopoulos that we looked at earlier in this presentation to account for the buckling of our longitudinal steel. We'll first find the S to dB ratio, so the ratio of our spacing of the transverse ties to the diameter of our longitudinal steel. The larger this ratio, the more likely it is for our steel to buckle. You can note that there are 3 different sizes of our transverse ties, so you need to use the appropriate transverse tie size with the S over dB ratio. After you calculate the S over dB ratio, you can approximate the post-yield behavior. You can either approximate it with a linear relationship or a bilinear relationship, depending on which one of the curves you're looking at. And note on this curve, we have the strain is normalized. So normalized by our yield strain and our yield stress. So 1 here and 1 here would be our yield stress and our yield strain. We can go from stress to force just by taking each of our components, our core, our cover, and our steel by the appropriate area. To go from stress to force in our core, we just use the area of our core only. To go from stress to force in our cover, we need to use our cover area. And remember, our cover area, we need to account for the cover falling off and spalling at a certain point, which we talked about a couple slides ago. And then with our steel, just our steel stress times the area of our steel. We can then combine these three force components to get the total force in our column. We can then plot our results from our table. Here is an example of the compression range for the column that we've been looking at in the last couple slides. You can see we have our cover falling off between 0.003 and 0.005 linearly. And you can see in this column, we don't have much confinement. So our confinement's not helping us much. So here we don't have any really gain in additional strength after our cover falls off. The last thing that I wanted to highlight in this presentation is some of the ACI 318 short compression member design limits. ACI 318 has two equations that cap the capacity for short compression members. And these equations essentially take into account accidental eccentricity that it just happens when you're applying an axial load on a column. It's really difficult to apply a load directly in the center of a column. And if it's anywhere off center, you'll be adding a moment to the column as well. So ACI has an equation for columns reinforced with spiral reinforcement and columns just reinforced with tie reinforcement, which have a 15% and 20% reduction in the overall column strength to account for this accidental eccentricity. You can see that using spiral reinforcement allows you to have less of a decrease in capacity, and this is because of the benefits that we saw that we can get with confinement using spiral reinforcement. So overall, spirally reinforced columns will behave better. And in seismic regions, you'll want to almost exclusively use spirally reinforced columns. Here again is a list of resources for further study on short compression members.